Okay, so let's go through this. Well, I wanna check something here. So number one, what does it mean for a language to be loosely typed and interpreted? So we talked about these things at the same time. So a loosely typed language is a language that does not require us to define what kind of value is being held inside of a variable. So we looked at that as, for instance, when we looked at C, C makes it say like int a equals 5, that kind of stuff. So we have to specifically define what kind of value a bucket is built for holding. So that's the loosely typed part of it, where it doesn't require us to do that. The interpreted side of this means that it's not compiled, so it tends to be relatively slow. It is executed at runtime, so everything is actually happening at runtime, which then translates into the slowdown. Something along those lines. So some people mention something along the lines of, they use the example I gave in class where like there's if somebody's giving a speech and you have an interpreter, there's a slowdown with that, things like that. That question was actually missed way more than it should have been. But, anything that was even kind of close, I pretty much tried to give points to. All right, number two, convert. I'm trying to think whose it was. Somebody in here did all the math right, but copied the numbers onto their paper wrong. Is that you?
Yeah.
All right, so let's see if I can copy them down right. So we have 100111101. All right, so we're converting that guy from binary into decimal. All right, so this is in the ones place. The twos, the fours, the eights, 16s, 32s, 64s, 128s. So this is 128 plus 16 plus 8 plus 4 plus 1. 157. Any questions on that one? I think most people got that one right. All right, next one. Convert 1328 from decimal to hex. One, 3, 2, 8 from decimal to hex. Oh, maybe Yaya can help us with this too. What base is hexadecimal?
That's another mistake.
So you did the math right on that one too. Just thought hexadecimal was base 8.
I just was, I just saw the 8 there and just immediately went divided by 8.
Gotcha. So hexadecimal is base 16, right?
Base. Too confident, but I was good.
Well, you did the math right.
I missed the easiest question.
Yeah, I gave you most of the points though. I only took off a little bit for. I laughed though. All right, so we're going to go ahead. We're going to divide this guy by 16. So that was the pattern we're really looking for there. So some of you got grossly wrong answers because you went this route. You multiplied the 8 times something, and then the 2 times something, and the 3 times something. That's not the pattern for converting from decimal to a base. So we take this number, we divide it by 16, so 1328. divided by 16 is an 83. So 83 times 16 is 1328, so that's a remainder of 0. 83 divided by 16 is 5. 5 times 16 is 80, so remainder 3. 5 divided by 16 is 0. 0 times 16 is 0 with remainder 5. Then you read your answer from bottom up, so it's 530. It's number 3, right? Okay. Let me jump over to Adam now for writing some of the code stuff, just so it does indentation and stuff nicer for me. That's fine. I'll just write it up top here. All right, so next one says, write the necessary code to display all the odd numbers between 1 and 100,000 to the screen. Okay, so we can say for I in range of 1 to 100,001 step by 2. That will do it. And then we can say print I. That's one way you could have written that guy. So start at 1, go all the way up to, but not including 100,001. So this will go up to including 100,000. But take steps of size 2. So that's one way you could have done it. Another way you could have said for I in range of 1 to 100,001, doing normal steps, if I mod 2 is equal to, we're supposed to do odds, right? All the odd numbers. If it's not equal to 0, then print out I. So that'll print out every other one. That'll print out only the odds. An odd number is a number that when divided by 2 has a remainder. All right, so something along those lines. This is probably the easiest one, although I don't recall anybody writing it that way. I think everybody pretty much had a question in there. You could have also written a while loop. I guess you could have said like I is equal to 1, while I is less than or equal to 100,000, print I is equal to I plus 2. Something like that would do it as well. Okay, so that is number 4. Number 5, what does the following function do? Give an example of sample input and output. So this guy takes in a list, and as long as there's stuff in the list, it's going to store the first value and then go through and check all the other values. Ultimately, this code returns the largest value in the list. That's what this code does. It returns the largest value in the list. Make sense? All right, number 6, write the necessary code to fill up a list with the even numbers between 1 and 100,000. Okay. So here, I'll just steal this guy. We'll start off at 2 there. And I'm going to give myself a list. So something like that. Create an empty list, loop through all the values between 2 and 100,000, step by 2. So you go 2, then 4, then 6, then 8, and then append each of those values onto some list. Otherwise, you could have done something like this. List is equal to the empty list. If it is even, then append I. Something like that. All right, so this one was testing, again, can you do some loopy stuff? And do you know how to add stuff to lists? All right. Let's see. Number 7, write a function that takes a string as a parameter and returns that string in reverse. So we'll call this guy reverse string. It'll take a string as a parameter, and we're going to create a new string. And we'll walk through the original string and build up the other one in reverse. So we'll say for I in range of length of string -1, keep going as long as it's greater than or equal to 0, take a step of size -1. So we'll walk through the string backwards. Each time through, we'll say answer is equal to answer concatenated with the current character we're looking at in S. So we'll walk S backwards, we'll build answer forwards. Each time through, we'll take the current character we're looking at in S and concatenate it onto the end of answer, which should build it in reverse. Make sense? Okay. I did give people credit as well if they used the built-in reverse function. It wasn't my intention, but if you used it, that's fine. Let's see. Number 8, what does the following function do? So this guy, let's see, takes in a string, and this adds up all the values in that string. So the for loop is going to go through all of the elements in S, and it's going to create a variable named A, start off at 0, so we're summing up a bunch of stuff, and we're going to get the integer version of each element in S and add it onto our sum. So presumably this would give us like the sum of all the Unicode values in the string, something like that, but it sums up all the integer version of all the elements in the string. Okay, number 9, write a function that takes 2 integers and returns the larger of the 2 integers. Def find max, maybe takes in an A and a B. If A is greater than B, return A. Else, return B. So this will return A. If A is bigger than B, it'll return B otherwise. If it's a tie, it'll also return B, but it doesn't matter. They're the same value. A couple people wrote something like this. They said, elif B is greater than A, return B. This isn't quite right, because this doesn't handle the case of when they're the same. If A and B are the same value, this would never return anything. Yeah, you need another else, or so you could just pick what you want to return here because they're the same at that point. All right, so is that all of them? Oh, last one. What does the following function do? Give an example. Do something. S1, S2. Okay, so this guy is doing string concatenation stuff. So if the length of S1 is greater than the length of S2, so if you have 2 strings coming in, if the first string is longer than the second string, it's going to concatenate the second string onto the end of the first string. Otherwise, if the second string is the longer of the 2, it'll concatenate the first string onto the end of the second. So for example, if the inputs were Mike and Lippman, since the second string is longer, it would have built that result. The second string followed by the first string. So the longer string will be first, the shorter string will be concatenated onto the end of that. Make sense? All right, so Any questions on the exam? If you have something specific about the grading of your exam, come up during the break or something, and I'll explain why I took points off. But in terms of the solution here, any questions about the exam? Okay, so now let's look at our homework. So we were writing tic-tac-toe, right? And I gave you, actually I gave you a lot of it, right? You were supposed to write whether there was a winner. I gave you play game. So while there's not a winner, we display the board. We make a move between the whoever the current player is, player 1 or player 2, so the X or the O's. If the current player was 0, we flip it to 1. If it was 1, we flip it back to 0. That allows us to decide who's going next, the X's or the O's. And then at the end, we want them to see if they want to play again and clear the board if they do. Okay, so let me run this real quick. I just want to see what the thing does right now. I think it just lets you fill in the board but never declares a winner, right? Okay, this is CSC535. There, where does this guy live? Downloads folder. Oh, that's not the right one. It should be underscore. All right, so what row do we put X in? So we'll say row 0. What column? We'll say column 1. And that puts it there, so then it goes and plays the game, right? Okay, so we need to write a couple of things here. So first, let's go ahead and write is winner. So there are, we can win this way, this way, this way. So 3 ways there, 3 ways up and down, or the 2 verticals, right? And we're looking for them to be the same values, but not underscores. All right, so we're looking for what's the best way we can check this. So this gave us practice with conditionals and gave us practice with ands and things like that. Ands and ors. All right, so one way we can win is if a row, so for instance, row 0 has all X's in it or all O's, or all O's in it, no underscores. Okay, so let's write that. And our board is stored, so this will be row 0. So what I'm going to go ahead and I'm going to create several variables here just to keep these separate. So I'm going to say row 1 winner is equal to, we can say board at position, actually this is row 0 winner, right? Board at position 0, 0 equal to board at position 0, 1 equal to board, actually that's going to be, so those guys are equal to each other, and board at position 0, 1 is equal to board at position 0, 2, and board at position 0, you could say any of them, 0 is not equal to an underscore. So all those things need to be true. The board at 0, 0, so row 0, column 0 is equal to row 0, column 1. and row 0, column 1 is equal to row 0, column 2, and row 0, column 0 is not an underscore. That makes sense? That'll handle a horizontal win on row 0. So we're making sure that we haven't just accidentally matched underscores, but we've made sure that that all three columns match each other. So it's whether they're X's or they're O's, but they definitely can't be underscores. All right, so that's for row 0 winner. Row 1 winner is row 1. So just change all these to 1s. Row 2 winner, change all these to 2s. All right, so let's just stop it there. Let's allow us to have a winner on our rows. Let's just test it up to that point. All right, so we're going to return. Right now, we're just returning false. Instead of returning false, I want to return row 0 winner or row 1 winner or row 2 winner. If any of those are true, we have a winner. Make sense? All right, so if any of those are true, if row 0 winner or row 1 winner or row 2 winner, if any of them are true, that means that we won on the last move. When are we checking to see if there's a winner? We're checking right here for is winner. So if there's a winner, since after we make a move, we flip the player. Then we roll back up. If there is a winner, who won? It was the player that went last. Okay? So when we fall out of this, loop, that means there's finally a winner. And the winner is the guy who's not the current player. All right, so that is current player, whatever cur player is. If it's a 1, we'll add 1 to it. 2, mod it by 2 will be 0. If it's a 1, or if it's a 0, we'll add 1 to it, mod it by 2. It's still 1. So we can go ahead and say print moves at position cur player +1. I'll put that parentheses here. Mod 2. So that'll switch a 1 to a 0 or a 0 to a 1. We could also put this in an if statement if we wanted to. But that takes us back to the previous player. Wins. Something like that. All right, so let's see this work. So we're only handling the horizontal wins right now. All right, so we'll go row 0, column 0, row 1, column 0, row 0, column 1, row 1, column 1, and then we should win on this next move. So we'll say row 0, column 2, X wins. That was the guy who just made that last move. We didn't actually show the board again, but we would have had X winning there. Make sense? And if we test it, just to make sure the mod thing works, I'll go ahead and win again. So we'll say row 0, column 0, row 1, 0, 0, 1, 1, 1, and then I'm going to say 2, 0, and then I'll say 1, 2, and we have O wins. All right, so understand what we did, this little trick that we just did right here. Since we know the previous player must have won if this while loop has ended, or there's a tie, potentially, but let's just deal with winners right now. If the previous player won, that means we take whoever the current player is, we add 1 to it. So if the current player is a 1, we add 1 to 1, and that gives us a 2. 2 mod 2 is 0. So that flips a 1 to a 0. Similarly, if the current player is 0, we add 1 to it, it's a 1. 1 mod 2, 2 goes into 1 0 times with a remainder of 1. Current player, the guy who won, is player 1. So this logic right here is an alternative to this if-else structure here. We could write an if-else structure here and say if current player is, I'll just show you the equivalent. If current player is 0, print moves at bucket 1 wins. If current player is 1, moves at bucket 0 wins. So this line right here is equivalent to this if-else structure, just by using the little modulus trick here. Make sense? And one's just as good as the other. I mean, tactically, this is a little bit slower, but if this makes way more sense to you than doing a mathy thing like this, that's fine. Do the one that makes more sense. Okay. So that handles our horizontal wins. Now let's do, go ahead.
I have another solution.
Okay.
Like for row in board, if row 0 equals to row 1 and row 1 equals to row 2 and it is not equal to underscore, it should be true. And then we could just print the winner as row of 0. That will be.
Well, yeah, okay, that's fine. But the difference here is that you're checking that here. So that means you would check your winner inside. You would print who won in here.
Before return true, we could print out the winner.
Yeah. You were printing your winner here.
Yeah.
Where I'm down here, I'm determining who won based on the last move that was made. That's fine. They're effectively both the same. Okay. So now let's make is winner work for other. So let's make it work for our columns. So we'll say col 0 winner. So this is if we have board row 0 column 0 is equal to board of row 1 column 0 and board at row 1 column row 1 column 0 is equal to board at row 2 column 0 and board at row 0 column 0 is not equal to the underscore. So that is the winner on column 0. Column 1 winner. Change that to a 1. 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 Call 2 winner. Change that to a 2. 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 All right, so this should get us our column winners now. So then we're going to return if we have a winner on row 0, row 1, row 2, or call 0 winner, or call 1 winner, or call 2 winner. That make sense? So that'll work for all the vertical wins. Let's go test this. All right, so we'll have 0, 0, 0, 1, 1, 0, 1, 1, and then row 2, column 0, X wins. Okay, so that handles the verticals. So now we need to do 2 more for our 2 horizontals. Not horizontals, our 2 diagonals. So we'll have we'll call diag 1 winner. All right, so this is going to be board at 0, 0 is equal to board at 1, 1, and board at 1, 1 is equal to board at 2, 2, and board at 0, 0 not equal to the underscore. So upper left hand is equal to the center, center is equal to the bottom right, and the upper left hand is not an underscore. So that's diag 1 winner. Diag 2 winner is board at, so this is going to be the lower left. So board at row 2, column 0 is equal to board at 1, 1, and board at 1, 1 is equal to board at 0, 2, and board at, just pick something along, that's in there. So board at, just to keep it consistent what we did before, row 2, column 0 is not equal to the underscore. All right, so that's our diag 1, diag 2 winner. So then we'll toss that in here. So or diag 1 winner or diag 2 winner. All right, so let's test that is winner on the diagonals. All right, so we'll go 0, 0. Then we'll do 1, 0. Then we'll do 1, 1. Then we'll do 0. Oh, I just pressed enter. I didn't type in a number. Let's try this again. 0, 0. Then 1, 0. Then 1, 1. Then 2, 0. Then 2, 2. And we have X wins there. And let's just test our other diagonal. So we'll say 2, 0. Then we'll say 0, 0. 1, 1. And then 0, 1. And then we'll say 0, 2. And X wins on the other diagonal. Okay, so that gets us all of our diagonals. What about checking for a tie? Because a tie should also, if you didn't check for a tie, that's not the end of the world, but a tie should also get us out of the loop. Because so they can't make a legal move, right? Because in order for them to make a legal move, they have to be trying to move into a place that has an underscore. And if there is no legal moves to make, then we need to let them start over. All right, so let's write the logic for whether a move is legal. So here we're letting them make a move where we give them the row and we ask for the row and column, and then we just haphazardly make that move, right? Well, we want to kind of make sure that the move that they're making is A, a legal move, but B, a move that they're allowed to make. Couple ways we can pull this off. What does it mean for a move to be legal? Well, it means that the row has to be greater than or equal to 0 or less than or equal to 2. So if row is greater than or equal to 0 and row is less than or equal to 2 and col is greater than or equal to 0 and col is less than or equal to 2. All right, so at that point, if we're still kicking here, since these are all ands, we know that row and column are at least legal places on our board. Correct?
So a quick question.
Go ahead.
What if we assumed that the inputs we're going to be getting were originally legal? And we just checked.
Well, that's fine. That's fine. You're just checking whether the underscore was there or not.
Yeah.
Yeah, that's fine. Yeah, I'm being overly. The error checking is not like a major portion of your grade. The rest of the logic is the real stuff. So I'm just being verbose here. So we're saying if all this is true, that means they at least gave us legitimate numbers. Okay? Now we need to say, is the number, assuming the number they gave us is legitimate, is it a legal move? That means that and board at row col is not equal to an underscore. If all those things are true, if they gave us a numerically reasonable number and the row column that they chose is not an underscore, then we'll go ahead and let them make the move. Else, we're going to say print illegal move. And then we'll go ahead and say display board. We'll show them the board again, just so they can refresh their memory as to what the board should look like. All right. But now we want to keep asking them for this stuff over and over and over again. Now we have a couple of options we can do here. After I display the board, one way we can do this is if they made an illegal move, I'll go ahead and display the board, and then I'm going to ask them to make a move again, right? So I'll say make move. And I'll pass it move val and the board. Because that's how we make a move, is by calling the make move function, right? Now, what's wrong with doing this? This will work. But if I'm calling this entire function again, okay, did we mention recursion last time? Okay, we didn't. We did a little bit with it, right? We did the factorial with recursion. Okay, so this is making a recursive call. I'm calling make move recursively, but this isn't really a recursive problem. So by calling this recursively, it will work, but I'm having to store all this information and put it on hold before we can make our next move. So while this isn't incorrect, it's not very memory efficient. The better thing for us to do here would be so typically we would say that infinite loops are bad ideas. So an infinite loop is a loop that never ends, right? So if I were to write something like while true, do this stuff, by definition, that's an infinite loop. True will always be true. So that's never going to change. But I have my get out of jail free card here called break. So what I can do here is I'm going to say, look, until I say otherwise, we're going to keep looping. What are we going to do? We're going to ask for the row. We're going to ask for the column. We're going to see if it was legal. If it was, we'll go ahead and let them make the move, and then we'll break out of that loop. Loop ends. Otherwise, we're going to print illegal move, display the board again, let this guy naturally spin back up, ask him for the row, ask him for the column, blah, 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 blah. All right, so this would be one way of writing this. If you don't like the while true thing, we can maybe make a variable here called made move and set this guy equal to false. And then maybe say while made move is equal to false, keep doing this. The better way of writing this would be while not made move, but this is going to make them more, going to read better for most of you, I think. So while made move is equal to false, we'll ask them for all this stuff. If we let them make the move here, then we'll say made move is equal to true, so that the next time we loop around, it'll fail. This while loop will end, and we'll drop out. Otherwise, we'll say illegal move, display the board, it'll spin back up, made move will still be equal to false, and we'll ask them for it again. So this guys, we're short-circuiting the while loop the next time by changing the value. Break just gets us out of the loop. So this is probably the better solution in terms of good programming practice. Typically, you would find books say that loops that say while true, things like that, infinite loops that look like infinite loops are bad programming practice. I think that there's a place for them, personally. Why should I have to create an extra variable here to accomplish what I wanted to? But same solution. So you pick the one that you like the best. This is probably the one that would not get a lot of complaints. Something along those lines. All right, so this ensures that the people are making a legal move. Okay, but this also presumes that there are legal moves left on the board. Right? How do we know when there's been a tie?
The most obvious one is to determine if there are no more spaces to play anymore.
Okay.
And there is no winner.
And how do we do that?
You can just go through the board and determine if there is still any underscore spaces on the board. You can just loop through it.
Okay. You think of a better way of doing it?
Right, like that's like the most basic way. But then if you want to go through the complicated way to check if there are any other moves that can still end up in.
I think there's still a more basic way.
In total, there are 9 moves, right? So
Yeah.
every time we place a X or 0 there, if we decrement the 9.
Yeah, just count. How many moves have been made? Okay, if we've made 9 moves and there isn't a winner, we're out of moves. Okay. That's a tie game right there. Make sense? So what we'll do here is after we make a move, let's go down to play game. We'll call this guy num moves. And we'll start, so you mentioned you can decrement it or you can start it off at 0 and count up to 9, whatever you want to do. So maybe you can do something like this. Let's do the decrement thing, but we'll call it moves left. And we'll start that guy off at 9. So now after a player has made a move, then we're going to say moves left is equal to moves, minus 1. So we'll decrement the number of moves that are left. Okay? Now, the next time through here, if there's a winner will be declared. But before we allow them to make another move, we want to ask a question. If moves left is equal to 0, which means we have no moves left, then we want to print out tie game, and we'll break out of our while loop. All right, so that'll get us out of the loop, as if there was a winner. Now, one thing we could do This logic's actually a little funky right now because of where we print out the winner. This is where your solution would have been better, printing out the winner inside of his winner. Because if we're out here, right now I'm outside of my while loop, we're in the situation where like, we're assuming there's been a winner. But there might not be. It might have been a tie. And we can't necessarily look at how many moves are left. Because even if there's 0 moves left, they might have won on the very last move. Does that make sense? Go ahead.
So if we have all the rows, row 1 winner or a row 2 winner, so can we check if it is not equal to the same XOR row? So so we have 8 possibilities, right?
Yeah.
Chance of winning. So for first possibility, it is not equal to O or X, then we can declare it is a tie for all the winning choices.
Yeah. Well, I think we can do that. I think that just to finish this up, I mean, the easiest solution here is just going to be to do this. After we're out of this loop, we can just say if is winner board, then print there was a winner. Because when we're out of this loop, there's 2 different reasons we could be outside of this loop. One reason is there was a winner. The other reason is there was a tie. So I'll just ask an extra time, was there a winner? If yes, we'll print out who won. Otherwise, we had already handled the tie game. If we want to handle them both out there, we can go ahead and just break there and then say else print. Did I copy it? I think I might have copied it. Tie game, like that. So we are outside of this while loop for one of 2 reasons. Either somebody has won or we ran out of moves. Make sense? So then we'll just do the catch-all down here saying, look, if there was a winner, we'll print out who won. Otherwise, must have been a tie game. Make sense? All right, so let's go check for our tie game. Make sure that guy is working. Okay, well, actually, let's test for illegal moves, too. So I'll say row 3, column 10. Illegal move. Doesn't like that. So we'll say row 0, column 0. It still didn't like that. Row. Bad logic. If row is greater than or equal to 0. Oh, no, we're getting the integer version of it. That's fine. If row is greater than or equal to 0 and row is less than or equal to 2 and col is greater than or equal to 0 and col is less than or equal to 2 and board at, oh, and it's equal to an, it's legal if it's equal to an underscore, right? I was checking to see if it was not an underscore. We're allowed to place an X or an O there if there is currently an underscore there. So I have my logic upside down there. All right, so 0, 0. Let me give an illegal move and then I'll fix it with the correct move. So I'll do 12, 11 or something like that. There's my illegal move. So then we'll do 1, 0. Then we'll do 1, 1. Then I'll do 0, 1. Then I'll do 0, 2. Then I'll do, whose turn is it? Oh, what row? Okay, so we're going to do 2, 0. You got to be careful you don't accidentally win. Then we're going to go 2, 1. Then we'll do 2, 2. And finally, we will do 1, 2. And there's our tie game. Okay. Anything else we were supposed to do? Oh, ask them if they wanted to play again. Right? All right. So now we're going to ask, do you want to play again? All right, and then we can use that the end equals thing, right, that we did up here to make sure it doesn't kick it down the line if you care about how it looks. So would you like to play again? Then we'll read it in. So I assume they're going to, here, let's just give them an option. We'll say Y or N, something like that. Now we need to read it in. So we'll say answer is equal to input. So that's going to be our what they typed in there. Then we'll ask if answer is equal to Y. If we want to be, we could also say if answer is equal to lowercase y, if either of those is true, then we'll let them play again. But what I'm going to actually do here is I'm going to say if they said no, then I'm going to break. And what am I actually breaking out of? I'm going to steal all this. All right, so I put all that underneath there. So we reset cur player. So if they entered no, they don't want to play again, we're going to break out of that loop. Else, we need to go ahead and reset the board. So we have a clear board, right? Like that. And then we also need to set moves left back to 9. Okay. And then the cur player will start back off at 0 the next time around. So that should let them play indefinitely. So after there's been a winner, would you like to play again, Y or N? If they enter in any sort of kind of N, we'll go ahead and break out. Game's over. You know, we could even give them a little print goodbye. Otherwise, we'll go ahead and clear the board. We'll reset our moves left, spin back up, reset the player's starting position, and then play again. All right, so let's test this. So we'll go 0, 0, 1, 0, 1, 1, 2, 0, 2, 2. So we have a winner. Would you like to play again? So we'll say Y, spins back up. Let's get ourselves a, I kind of hate ties. I don't, ties are hard to get. Okay, then we're going to do 0, 2. Then I need to block. So I'm going to do 1, 2. Then I need to block. So I'm going to do 1, 0. Okay. Then it's O's turn, so I need to block. So I'll do 0, 1. And then I'll block. That's 2, 1. Tie a game. Would you like to play again? I'll put an N this time. It says goodbye. Reasonable enough solution? All right. Anything else we were supposed to do there? Or is that all the homework assignment? So I'll take that, throw it up on Slack. Okay, so that's up there. Now, let's go to the book here. All right, I'm going to start talking about classes today. So I'm going to spend a few minutes introducing them right now, then we'll take a break and we'll come back and we're going to write something using classes. All right, so this goes back to our example from when we were, kind of first week of class when we talked about procedural programming languages versus object-oriented programming languages. So what did languages like C++ give us that C did not? So remember when we talked about C, we said it had things called structs, and that only allowed us to hold name-value pairs, kind of like dictionaries. Whereas in C++, we now have this new organizational unit, this new, this new way of organizing our data into something called a class. So a class allows us to have name-value pairs similar to what structs or dictionaries let us have, but it also allows us to have functions associated with it. All right, so I'm going to swing past a lot of this stuff and just get down to the syntax. I'll have you go through and read some of that stuff. All right, so here's an example. So we're going to have a class. So we use the keyword class to make this. Then we give the name of it. And then inside here we have something called a constructor. So let's talk about that just for a few minutes. So I'm gonna go for about another 5 or 10 minutes, and we'll take a break, and then we'll come back. But let me at least introduce objects here. So we'll call this objects. So objects use the class keyword. They contain what are called fields. Let's call contain fields, constructors, and methods. So fields are variables owned by the class. Constructors are the initializers for creating an instance. I'm going to actually capitalize that because that's a word we use quite a bit. An instance of a class. And methods are what we know them to be. They're functions. So we can, if you want to use Python, it calls them all functions. But typical object-oriented nomenclature calls them methods. But whatever. So these are the reusable chunks of code, like we've been writing for a while, right? All right, so those are the things that go inside of objects. So if we look back here, we see they're creating a class called time. And time has two fields here, one called hours and another one called minutes. All right, now what I'm actually going to do, well, here, let's just follow this along here. So class time, our constructor must look like this. So it's kind of a very special, that guy is how constructors always look. Let me kind of explain it in an interesting way, I think. Okay, so a constructor is always going to be def, forget about case sensitivity here, underscore, underscore, init, underscore, underscore, open parenthesis, self, then a colon. I'll make this lowercase d. Okay, so what is a constructor? Okay, a constructor is a special kind of function that does any initial setup of fields for the object. Okay? So it's our initializer, hence the init thing. All right, but now let's talk about this keyword self here. All right, so self. In other languages, self, other names for self. Some languages call it this. Some languages call it me. Actually, that's just Visual Basic calls it me, which is actually kind of accurate when you think about it. But the definition for this guy is how an object refers to its self from within itself. All right? So when I'm talking to people, I don't say Mike. I say me. When I'm referring to myself, I refer to myself as me. So from within myself, I refer to myself as me or self. Okay? That's what self or this or me is, depending on what programming language you're working with. It's how an object, so I'm an instance of a human, right? It's how an object refers to themselves from within themselves. Okay? Externally, okay, you guys wouldn't point at me and say self, right? You would point at yourself and say self. You would point at me and say Mike, okay, or teacher, or professor, or whatever, you know, not self, anything but self. That's something else. But when we point at ourselves, that's when we're talking about self. So when we are inside of an object here, when I'm initializing this object, he's creating here two fields, one for hours and one for minutes, and he's setting the hours and minutes initially to 0. So he's setting his hours, self.hours to 0, self.minutes to 0. All right, so if I assume that I'm an instance of time, our time object here, when I first come into existence and my initializer gets called, I think about the two pieces of information I keep track of. I think about my hours and my minutes. So self.hours, self.minutes, and I go ahead and I initialize both of those to 0. Okay, kind of ready to go. Down here, this is us creating an instance of time. So I'm creating a variable named my time, and I'm setting it equal to, this is how we call the constructor for the time object. Notice the name of the class is time with a capital T. You pass in an open and closed parentheses in this case. You can have other things passed in here, but for the most simple case, it's always going to be self. I will come in here and we'll put like optionally, I'll put a little question mark there because you can pass other parameters to this guy if you want. And we'll see some examples of that here after we take a break. All right, but this line right here creates a variable named my time and sets it equal to an instance of time. And that particular instance of time will come with two fields that have both been set to 0. So hours is one field, minutes is another field. And those belong to each and every instance of time. So if I have my time and my time 2, both equal to the time constructor, I have two separate objects. One of them has their own self.hours and self.minutes. The other one will also have self.hours and self.minutes. Okay? And then for my time here, if I want to change hours to 7 and I want to change minutes to 15, I can do that. Okay? So, as just a general introduction, does that kind of make sense how the syntax for objects works? All right. So let's take, 30 seconds? Let's take about, what do we got here? Let's take 8 minutes. And then we will, I'll take 10. Take 10 minutes, come back at 7:25. Come back at 7:25 and we will pick up where we left off.